Hello, my name is Megan Overholt, and today my group and I will be discussing non-parametric statistics. Non-parametric statistics are used when the population from which the samples are selected are not normally distributed. The first non-parametric statistical test we will be discussing is the simplest, the sign test. The sign test for a single sample is a non-parametric test used to test the value of a population median. When using the sign test, the researcher hypothesizes the specific value for the median of a population, then selects a random sample of data and compares with the conjectured median. If the data value is above the median, then a plus sign is assigned to that data value. And if the data value is below the assigned median, a minus sign is assigned to the data value. If the data value and median are the same, 0 is assigned. If the null hypothesis is true, the number of plus signs equals the number of minus signs. If the null hypothesis is not true, then it will be disproportionate. There are two cases for using the sign test. If n is less than or equal to 25, the test value is the smaller number of plus or minus signs. When n is greater than 25, the test value is z equals x plus 0.5 minus 0.5 times n divided by the square root of n divided by 2. X equals the smaller number of plus signs and n equals the total number of plus signs. Below is the steps needed to determine if you should accept or reject the null hypothesis. We will go over this in more detail later. There is also a paired sample sign test. This sign test can also be used to test sample means in a comparison of two dependent samples. When the condition of normality cannot be met, the non-parametric sign test can be used. The paired sample sign test is a non-parametric test that is used to test the difference between two population medians when the samples are dependent. There are two assumptions for the paired sign test. The first one is the samples are random. The second one is the variables are dependent or paired. Now we are going to go over an example and work through the steps of how to complete a sign test. The example is the median age at first marriage in 2010 for women was 26.1 years, the highest it has ever been. A random sample of women's ages from recently applied for marriage licenses resulted in the following set of ages. At alpha equals 0.05, is there sufficient evidence that the median is not 26.1 years? Below you will find a table of the data that was selected. The first step in the procedure table was to state the hypothesis and identify the claim. Since we are trying to discover if the median age is not 26.1 years, that will be our null hypothesis and also our claim. Step 2 is to find the critical value. You will subtract the hypothesized median, which is 26.1 years, from each data value in the table. So for example, 34.6 minus 26.1 equals 8.5. So we assign 34.6 a plus sign. 25.9 minus 26.1 is negative 0.2. So we assign 25.9 a negative sign. After subtracting each hypothesized median from each data value, we have discovered that there are 11 plus signs and 4 minus signs. Since n is less than 25, you will use Table J in Appendix A of your book. Since there are no zeros, n equals 15, and the alpha is 0.05. So once you go to the table, you will see that at 0.05, in a two-tailed test, at n equals 15, the critical value is 3. Step 3 of the process is to compute the test value. Since n is less than 25, the test value is the smaller of plus or minus signs. In this case, there are 11 plus signs and 4 minus signs. The test value is 4. Step 4 of the procedure table is to make the decision. We will compare the test value 4 with the critical value of 3. If the test value is greater than the critical value, the decision is to not reject the null hypothesis. In this case, the null hypothesis is not rejected since the test value is greater than the critical value. Finally, we will summarize the results in Step 5. There is not enough evidence to reject the null hypothesis that the median age at first marriage is at least not 26.1 years. This concludes my example of a non-parametric test. Next is another example of a non-parametric test, the Wilcoxon rank sum test.
My name is Denise Bell, and today I will be discussing the Wilcoxon rank sum test. The Wilcoxon rank sum test is also known as the Mann-Whitney test. The Wilcoxon rank sum test is a non-parametric test that uses ranks to determine if two independent samples were selected from populations that have the same distributions. The hypothesis statements function the same way as the two-sample Z and T test, but here we are focused on the medians rather than the means. Assumptions for the Wilcoxon rank sum test. There are two conditions that must be met. First, the two groups being tested must be independent of one another. The size of each sample must be greater than or equal to 10. Listed below is the formulas for the Wilcoxon rank test. R is equal to the sum of ranks for smaller sample size. N1 is equal to the smaller of sample sizes. N2 is equal to the larger of sample sizes. And it should be noted that if both samples are the same size, you can use either one for N1. The steps for the Wilcoxon rank sum test are listed below. First, you want to state the hypotheses and identify the claim. Second, you want to find the critical values. Next, compute the test value, make the decision, and summarize the results. Example I use is a dietitian wanted to see if there is a difference in the number of calories consumed by professional female weight trainers and endurance runners. And alpha equals 0.05. Is there a difference in the number of calories consumed? Here's the table comparing a runner caloric intake to weight trainers. Step 1, we want to state the hypotheses and identify the claim. The null hypothesis is there is no difference in the amount of calories consumed by female professional runners and weight trainers. The alternative hypothesis, the claim, there is a difference in the amount of calories consumed by female professional runners and weight trainers. Step 2, we want to find a critical value. At alpha equals 0.05, this is going to be a two-tailed test. The critical values used are positive 1.96 and negative 1.96. Step 3, we want to compute the test values, and this involves multiple steps. First, we want to combine the data from the two samples, arrange the combined data in ascending order, and rank each value. We need to indicate the group. Here in the table, I have the calories in ascending order. Have the group R is equal to runners and WT is equal to weight trainers, and I ranked them. Step 3 continued. We want to sum the ranks of the groups with the smaller sample size. So in this case, they both had the same sample sizes, so we can use either group. The sum of ranks is equal to 211. Next, we want to substitute in the formulas to find the test value. And here we find that the Z is equal to 7.96. Next, we want to make the decision, and here the decision is to reject the null hypothesis because the test value 7.65 is greater than the critical value of 1.96. Next, we want to summarize the results. There is enough evidence to support the claim that there is a difference in caloric intake between female professional runners and weight trainers. And next, we will be talking about the Wilcoxon sign rank test.
My name is JC Henson, and I'm going to tell you about the Wilcoxon sign rank test. The Wilcoxon sign rank test is used for dependent samples to compare distributions. This test does not require the condition of normality. The textbook definition is the Wilcoxon sign rank test is a non-parametric test used to test whether two dependent samples have been selected from two populations having the same distribution. The following assumptions must be met before the Wilcoxon sign rank test can be used. First, the paired data have been obtained from a random sample. And second, the population of differences has a distribution that is approximately symmetric. Procedures for the Wilcoxon sign rank test. Step 1. State the hypothesis and identify the claim. Step 2. Find the critical value from Table K when n is less than or equal to 30, and from Table E when n is greater than 30. Step 3, when n is less than or equal to 30, first you're going to make a table as shown. You're going to have the before column, the after column, difference, absolute value, rank, and signed rank. Step 3 continue. Next, find the differences before and after, denoted by XB minus XA, and place the values in the differences column. Find the absolute value of each difference and place the results in the absolute value column. Rank each absolute value from lowest to highest and place the rankings in the rank column. Give each rank a positive or negative sign according to the sign in the difference column. Find the sum of the positive ranks and the sum of the negative ranks separately. Select the smaller of the absolute values of the sums and use this absolute value as the test value, W. When n is greater than 30, you're going to use Table E and the test value. Step 4, make the decision. Reject the null hypothesis if the test value is less than or equal to the critical value, and then summarize the results. In this example, the study assessed the effectiveness of a new drug designed to reduce tremors in patients diagnosed with Parkinson's disease. There are 5 patients. These scores were their tremors before treatment. This was after 1 week of treatment. First, we compute differences scores for each patient. And that was added in this column. The next step is to rank the different scores. First, order the absolute values of the difference scores and assign rank from 1 through n to the smallest through largest absolute values of the different scores, and assign the mean rank when there are ties in the absolute values of the different scores. The final step is to attach the signs, positive or negative, of the observed differences to each rank as shown below.
Hello, my name is Allison Owens, and today I will be explaining the Kruskal-Wallis test. The Kruskal-Wallis test, also known as an H-test, is a non-parametric test used to compare 3 or more means. When performing this test, we have 2 main assumptions. The first assumption is that there are at least 3 random and independent samples. Our second assumption is that the size of each sample is 5 or greater. When performing a test, we first collect all data values and assemble them into groups and rank. Next, ranks are separated and H is computed. If samples are from different populations, the sum of the ranks will be different and H will be a larger value. If samples are from the same population, the sums of the ranks will be about the same. Finally, we use the distribution that is approximated by using the chi-squared distribution k minus 1 equals degrees of freedom. The following steps are used to complete an H-test. The first step is to define the null and alternative hypothesis. Step 2 is to state the alpha. Step 3, calculate degrees of freedom. Step 4, state the decision rule. Step 5, calculate the test statistic. Step 6, state the results. And finally, step 7, state the conclusion. Now we will work through an example problem together on how to conduct an H-test. A math teacher wishes to see if the total score on a particular math exam between 3 classrooms randomly selected in a school is the same. At alpha equals 0.05, is there enough evidence to reject the claim? Listed below is the table with our data. As you remember from the previous slides, there are 7 steps to complete an H-test. The first step is to define the null and alternative hypothesis. The null hypothesis for this example is there is no difference between total scores on a particular math exam and classes. The alternative hypothesis is there is a difference between total scores on a particular math exam and classes. Step 2 is to define the alpha. Alpha for this problem is 0.05 as it is listed in the example problem. The next step in conducting our test is to determine the degrees of freedom. The equation to determine degrees of freedom is k minus 1, where k stands for the number of groups. In our example, we have 3 groups. Subtract 1 to get 2 as our degrees of freedom. Step 4 is to state the decision rule. To determine the decision rule, first we would look up the chi-squared distribution table, which can be found in the textbook Elementary Statistics, a Step-by-Step Approach, under Appendix A, Table G. Using our degrees of freedom, an alpha value of 0.05, we can line up the values to find that the chi-squared distribution is 5.99, meaning if the chi-squared value is greater than 5.99, we should reject the null hypothesis. Step 5 in our example is to calculate the test statistic. In order to determine our test statistic, first we will take all of our values from our test scores and rank them in order from lowest to highest score. Lowest score getting a rank of 1 and highest a rank of 18. The equation listed is the equation used to determine our test statistic. Continuing with step 5, we will next determine the variables used in the equation. Capital R equaling the sum of ranks, R1 equaling the sum of ranks for group 1, R2 equaling the sum of ranks for group 2, and R3 equaling the sum of ranks for group 3. Lowercase n equaling the size of the sample, n1 equaling the size of sample 1, and so on and so forth. Capital N equaling the sum of the size of the samples. To the right is a table with the values of each rank and the total sum of ranks for each group. Continuing with step 5, now that all of our variables have been defined, we can plug in the appropriate variables into the equation and compute our results. After computing the results, we can find that the H value is equal to 2.854. Our final step is to state the conclusion. Because the value 2.854 is less than the critical value listed from the table before of 5.99, we will not reject the null hypothesis. We can also state that there is not enough evidence to reject the claim that there is no difference between a particular math exam and classes. This concludes our example of how to conduct an H-test. Thank you.
My name is Caitlin Rife, and today we are going to talk about the Spearman rank correlation coefficient and the runs test from Chapter 13, Section 6. Chapter 10 provided us with the techniques for computing regression and correlation. The Pearson product coefficient was used to determine if two variables were linearly related. The values ranged from positive 1 to negative 1. The assumption for that product coefficient was that the hypothesis P was equal to 0, where the populations were normally distributed. But what if the requirements for the Pearson coefficient were not met? We could then use the Spearman rank correlation coefficient. The computations for the rank correlation coefficient are simple compared to the Pearson correlation coefficient. It involves ranking each set of data and finding the difference in ranks. RS is computed using the differences found. If both sets of data have the same ranks, RS equals +1. If both sets of data are ranked in the exact opposite way, RS is equal to -1. And if there is no relationship between the data, RS is equal to 0. The assumptions for the SRCC are as followed. Number 1, we can assume that the sample is a random sample. Number 2, we can also assume that the data consists of 2 measurements or observations taken on the same individual. One must check and see if the above requirements are met before they proceed with the problem. The formula for the SRCC is shown in this picture. D is the difference in ranks and N is the number of data pairs. This formula is algebraically equivalent to the formula that we used for R in Chapter 10, but the ranks are used instead of raw data. Looking at the test of significance for the SRCC, we can use the table L for values of n up to 30, and the normal distribution can be used for values larger than 30. The test can be left-tailed, right-tailed, or two-tailed. Hypotheses are p equals 0 and p does not equal 0, where p is the population correlation coefficient. Looking at the procedure table, the first step is to state the hypothesis. The second step is to find the critical value. Step 3, we want to find the test value. To find the test value, we make a table. The first step in that table is to rank the values in each data set, then subtract the rankings for each pair of data values, x1 and x2. You then square the differences, find the sum of the squares, and substitute that into the formula. Step 4 is to make the decision, and step 5 is to summarize the results. Let's look at example 13.6.1, Math and English exams. Use the following data to complete the Spearman rank correlation coefficient to find the difference in ranks between math and English exams. Row 1, we can see the math scores. Row 2, we can see the English scores. We move on and we mark down the English and the math scores. Then for columns 3 and 4, we want to put the ranks of the English and the math scores. For the first row, we can see that there is an English score of 56 and a math score of 66. The rank for the English score would be 9th. The rank for the math score would be 4th. The difference in those ranks is 5, and the difference squared is 25. We would complete the following procedures for the remaining rows. Then we would calculate the sum of squares. 25 plus 1 plus 9 plus 1 plus 16 plus 1 plus 1 are equal to 54. We then substitute into the main equation. Keep in mind that n is equal to 10 for the number of data pairs. We find that p is equal to 0.67. There's a strong indication of a positive relationship between the ranks individuals obtained in the math and English exams. How do we apply the procedural steps? Well, the test value that was calculated was p equals 0.67. First, a hypothesis would have been stated, and then a critical value for n equals 10 would be found in Table L and Appendix A of the text. The test value would then be compared to the critical value to make the decision of accepting or rejecting the null hypothesis. The fifth and final step would be to summarize the results that were found. Let's move on to the runs test. How do we know if the data we obtain from a sample are truly random? Well, the runs test is a method that we can use to determine that answer. A run is a succession of identical letters preceded by a different letter or no letter at all, such as the beginning or ending of the succession. Scenario 1. M is marked for male, F is marked for female. We can see here that 10 males are selected followed by 10 females, and the sample does not appear to be randomly selected. Scenario 2 also does not appear to be random because the selection is female, male, female, going on to the end of the problem. Each letter constitutes as one run. We can see here for run 1, we start at the beginning. We count 3 F's. Then we see 2 M's, and that starts the run 2. Once we get to the F, that is run 3. And we keep going, so on to the end, and we find that there are 11 total runs. The number of runs is used to determine the value of the test value. In this example, N1 represents the first category, 10 males, and N2 represents the second category, 10 females. The letter G is used to determine the number of runs, and in scenario 3, we see that G is equal to 11. Let's look at example 13.6.2. Determine the number of runs for the following situation in a selection of boys and girls for student aids to the teacher. We see here that there are 16 values. N1 is equal to 8 and N2 is equal to 8. We see that the number of runs is 9. We start with the first B, and that is the first run. Then we count 4 G's, which is the second run. 2 B's mark the third run. The single G marks the fourth. The single B is the fifth. 2 G's is the sixth. 2 B's is the seventh. The G is the eighth. And then the remaining 2 B's are the ninth run. The runs test for randomness is a non-parametric test that is used to determine if a sequence of data values occurs at random. It considers the number of runs compared to the frequency of the letters. For data to be selected at random, there should be not too few or too many runs. When the data is numerical, we use the median of the data to determine the number of runs. Find the median for the data, then subtract the median from each value. If the data is above the median, assign it letter A. If the data falls below the median, then we want to assign the letter B. Ignore data values that are equal to the median. The assumptions for the runs test for randomness include assuming that the data from the sample are arranged in order in which they were selected, and we can also assume that each letter, number, or event can be classified into one or two mutually exclusive categories. The formula for the test value for the runs test is as follows. When N1 is less than equal to 20 and N2 is less than equal to 20, we want to use the number of runs denoted by G as the test value. However, we want to use the formula when N1 is greater than or equal to 20, N2 is greater than or equal to 20, or when N1 and N2 are both greater than 20. Take a look at the procedure table. Step 1, state the hypothesis and identify the claim. Step 2, find the critical values. Table M is used when N1 and N2 are less than or equal to 20. Table E is used when N1 is greater than 20, N2 is greater than 20, or N1 and N2 are greater than 20. Step 3, find the test value. A states that we use the number of runs if N1 is less than or equal to 20 and N2 is less than or equal to 20. Use the formula when N1 is greater than 20, N2 is greater than 20, or when N1 and N2 are both greater than 20. Step number 4, we make the decision, and step number 5, we summarize the results. Let's take a look at this example when we select blue and green eye color from a school. In a school, a teacher wants to see whether or not the eye color of the student selected to raise the flag is random. She observes the first 20 with the following sequence of green, represented by letter G, and blue, represented by letter B, eye color. We can see the runs here, and we want to test the randomness of the sample at A equals 0.10. We can see here in step 3 that finding the test value is determining the number of runs. There are 8 runs. Step 4 is to make the decision, and the test value is between the critical values, so we do not want to reject the null hypothesis. Step 5, summarize the results. There is not enough evidence to reject the hypothesis that the students were selected at random according to eye color. If you look to the right here, we can see the run table. There are 8 runs, and each letter is broken down and put into each run. That concludes the Spearman rank correlation coefficient and runs test information that we went over today.